Hello everyone, welcome to High Performance Computing, Advanced Scientific Computing. This is lecture 8, Computational Fluid Dynamics. From this lecture, I will take over to continue the course, which this year is focused on the Computational Fluid Dynamics CFD. In the beginning, let's have a review of lecture 7, which was an introduction to deep learning. Of course, you have the details on the slide of the course, and also the recording is available with a lot of description. The lecture presented the TensorFlow and Keras environment and PyTorch. You saw how the activation function works. Also, you learned about the overfitting, underfitting, and why they are happening. Also, you saw a complex relationship between deep learning and high performance computing. You had some example from the convolutional neural network CNN and how it's working with the other variant of the LSTM, for example. In the second part of the course, which focus on the CFD, we will have some example of the application of deep learning in the fluid dynamic. And you will see these practical cases in upcoming lectures. Now, let's go on the lecture 8. This is outline of the course, and we are in the lecture 8, Computational Fluid Dynamic. This lecture will have two parts, and regarding the outline, in the first part, we will talk what is the computational fluid dynamic, about the background, a range of its application, about the Navier-Stokes equation in the fluid dynamic, and the numerical scheme used on the computational fluid dynamic. Then in the second part, we will see how CFD technique is applied. We will see the classification of the flow, solution method, meshing, boundary condition, and there are three main techniques using of the CFD capability to deal with turbulent flow, and we will talk in detail in this regard. First part is computational fluid dynamic. Fluid dynamic background. It's from many years ago. A short description of the fluid dynamic is a science of the fluid motion. Commonly, it's studied in one of the three ways: experimental, theoretical, and numerically, which is related to computational fluid dynamic. When we look at the antiquity, we can see example from the fluid dynamic like aqueduct, canal, harbors, bathhouses. One of the key figures was Archimedes. He had many inventions in the fluid dynamic area and many applications. For example, one of them is a water screw, which can be used to lift and transport water and granular materials. Also in the energy field, there are old wind turbine, and here you can see this figure from this type of the wind turbine. One of the oldest sketches also from Leonardo da Vinci is a gigantic explosion, which show the different scale and size of the eddy in the turbulent flow, which one of the complex phenomena in the fluid dynamic. This slide presenting the fluid dynamic from the past and recent years. Of course, there are many famous scientists had many achievements and great work in the fluid dynamic area. For example, from the 18th and 19th century, we have Bernoulli, Euler, Navier, and Stokes, which we have the great equation of the Navier-Stokes. And of course, we have Lagrange, which one of the great work he had, the Lagrangian framework. We have Laplace, which we're using the Laplacian in the to solving the partial differential equation. From the recent century, the 20th, one of the great area which has a lot of activity about the turbulent flow and boundary layer. Turbulent flow, one of the complex phenomena in the fluid dynamic, and is still a lot of focus on it. It's called unsolved problem yet. For example, regarding the boundary layer, Prandtl, he suggested the boundary layer concept to deal with this. Also, we have the von Karman state to study the flow when it's passing the object. About the turbulent flow, we have the Kolmogorov scale, which about the universal energy spectrum on the turbulent flow. We have the work from the bachelor, which about the theory of the homogeneous turbulence. And there are many details, of course, you can see in the literature. Regarding the CFD, there are some very great resources and book. One of them is a numerical heat transfer and fluid flow from the professor Patankar. This is one of the great book, and many of the great scheme for the CFD is available and explained in detail. Of course, the CFD is a very large area. Usually, when you want to be expert in the CFD, you need to pass at least this course, especially focus on the CFD. It has a different level from the introduction and advanced one. And every day also there are many new scheme and development in this area. But why HPC is really relevant to the CFD? Because the CFD is the computational approach, is numerical approach. We are dealing with the computational time. We dealing with the computational capability of the computer. So we need to be able to run this computing with the big machines, usually when we are dealing with complex problems. And we will see how they are working. Now let's see what is computational fluid dynamic. Usually in the fluid dynamic, when we are dealing the numerical approach to solve a problem, we need to discretize the domain of the problem to the small areas. This small area is called grid or mesh, and we have different approach for that. We have finite difference method, we have finite volume method, we have finite element method also. Indeed, the grid or the mesh must be sufficiently fine to solve the problem. Sometimes because of the complexity of the problem, because of the geometry of the problem, because of the boundary of the problem, to have the fine mesh, the computations will be so high. So we need to have high performance computing to run the simulation and solve the problem. We will see some example and why it's in this way we need to run it on the HPC. Indeed, before development of the high performance computing, many of the large problems were not be able to solve, and the high performance computing is helping too much to have the solution in the fluid dynamic area, especially for the 3D problems, and also about the turbulence flow and the combustion, which usually they are extensive computing. But why we are using the computational fluid dynamic or CFD? Indeed, when we are dealing with the fluid dynamic problem, there are three different approaches: the experiment, analytical or theoretical solution, and numerical solution. Numerical solution is related to computational fluid dynamics. When we are talking about the experiment is possible for a specific problem. We have limitation on the measurement. We require tools to solve the problem, and we are dealing with dissimilarity also about the scaling. However, the result from the experiment with different scale could be used to validate the result from the CFD. When we look on the analytical solution, it's for limited and simple problem, especially when the problem linear. It's costly to use the analytical solution. there is a lack of analytical solution for many problems. However, is present general solution equation for the problems. Now let's look on the CFD, the numerical solution. There is no limitation to solve the problem if we apply the sufficient method. It's reducing the computational and operational cost. We can apply it for the complex problem, for example, nonlinear, and also about the geometry. We can validate the solution before the application. Two items is required in the numerical approach. We need to have the detail of the boundary condition and initial condition, and also we are dealing with the computing time depend on the computer power. These a key parameter regarding the CFD, which is related to high performance computing. So that means sometimes for the computation, the computing time it's essential, and we need enough power to solve this type of problem. When we have the 3D problem, when we have large size of the problem, when we have complex phenomena like turbulence flow, which we need to have fine grid, it is essential to have high performance computing to solve this kind of a problem. CFD is comprised of math, fluid dynamics, and computer science. In the CFD, and we can say in the fluid dynamics, there are governing equation, which they are partial differential equation. We call them PDE. In the CFD, these equations are broken down into a set of algebraic equations obtained by discretizing the equation to a certain number of cells or points. We call them mesh or grid. Indeed, we're solving the problem for each grid or mesh, and then we collect all these solutions to get the solution for the whole domain of the problem. To get the equation of the fluid dynamic, we apply the first law of the thermodynamics and Newton's second law of motion on a fluid particle, and will give us three sets of equation: mass equation, continuity, momentum equation, and energy equation. When we have these three equations, indeed we have the Navier-Stokes equation, which is the main equation in the fluid dynamic to have a solution on the problem. This slide presenting the CFD application. We had this short review of the application on the lecture of the introduction to OpenFOAM. Of course, you can see many applications in industry about the energy, about the health system, and in the aircraft, in the automobiles, and indeed this show the importance of the CFD and how we can develop it. We will able to deal with many problems. One of the important concepts that in the fluid dynamic we have two different regime of the flow. It's called laminar and turbulence. Dealing with the laminar much easier than the turbulence flow, but most of the flow has a turbulent feature. So we can say we mostly deal with the turbulence flow. Then we need to have high performance computing to solve the real condition of the problems. And here you see also in this example also most of the flow is turbulence. For example, the example of the wind turbine CFD simulation is the example of the wake of the wind turbine, which has a turbulence behavior. Also about the SpaceX Dragon, about the aircraft, about the car simulation, also about the COVID-19 spread in the environment. Most of them, they have a turbulence structure, and we are dealing with the complex phenomena to solve this type of the problem. CFD is presenting a very nice and beautiful detail of the problem, and here you can see two examples of its application. There are many online resources and material. If you are interested, you can look on them, and you can see how the CFD helping us to see the detail of the problem and understand what's happening in the fluid dynamic area. To deal with the CFD also, it's essential to have software. Uh, in the previous lectures, we had example from the OpenFOAM, and also on the workshop from the Real-Scale Cloud Computing, you saw how we can use the OpenFOAM for the CFD with high-performance computing and run a simulation and solve a problem. Indeed, there are commercial codes like ANSYS Fluent, Applied Computational Fluid Dynamics, Azure, Fluid and others. Uh, and also we have open source or free codes like OpenFOAM, Calculix, CANS, which is from Pedro Costa. He's assistant professor at the University of Iceland and TUDEV. We have Dolphin, FluidSim, and others. It depends to the problem and the capability required. We can use these open code. Actually, the free and open source code, it's mostly used in the research because we are able to modify the code depending on the problem condition. And the commercial codes usually used for the engineering design and mostly applied in the industry. Usually the CFD code is a software include the solver, grid generation, and flow visualization. So when it's solving the problem, then we can visualize the result and we can see how it's working. From the OpenFOAM, you saw this example and how it was working to see about, for example, the motorbikes simulation. There are some other open source code for the CFD with a specialized, for example, the ALIA is a high performance computational mechanic code designed to solve complex coupled problems involving multiple physics, scale, and domains, and usually is using in the engineering industry. Also, the RBP is the dedicated LES, large eddy simulation. We will talk about the large eddy simulation in the next lecture. Large eddy simulation is one of the approaches is used from the CFD for turbulent flow problem. And as you can see here, also this code used for simulate the unsteady compressible flow in complex geometry, with or without combustion. The other one is a Basilic, is a free software developed at the CNRS Institute of the Ronald d'Alembert in Paris for solving partial differential equation on adaptive meshes. The multi-physics code, Maya, is previously known as ZFS, has been under active development for over 15 years at the Institute of Aerodynamics at Aachen University. Indeed, in some project that University of Iceland also collaborate, we are using these codes. There are use cases. For example, in the CO race project, you can, if you are interested, you can see this project and how this code helping to dealing with this specific problem, which is useful in the industry. For example, one of them is using to simulate the wake on the real size of the wind turbine, and also another one using to reducing the drag force on the wing of the aircraft. And they are one of the up-to-date research currently to develop this area. When we talk about the computational flight dynamic, in the beginning, it's come to mind that what about the computational resource? Indeed, the CFD has traditionally been one of the most demanding computational applications. And always it required a powerful computer. If you look on the history of the, for example, NASA, always when they started to uh, with a new project, there was primary thinking about the computing power, and sometime in the beginning, they had to build required computing power, and then starting to simulating the project. We have the single processor computers, vector computers, parallel computer. We will talk about them. We have the shared memory and distributed memory. You saw them in the previous lecture in this course. Indeed, the CFD is multidisciplinary. So we have the fluid mechanics, we have numerical analysis, we have the computer science for the CFD to able to solve the problem in the CFD. Then it's a collection of the different area to deal with these kind of problems. This slide it's presenting the multi-phase flow, how using the CFD in this area. Multi-phase flow has a broad area, for example, the spray drying, pollution control, pneumatic transport, slurry transport, fluidized beds, spray foaming, plasma spray coating, and many other areas. And you can see here how the CFD help us to understand these phenomena. For example, in the center of this slide, there is an example of the simulation for the gas liquid multiphase flow, and you see how we have different visualization. The sphere are from the gas, and in the water and the liquid environment. Also, you can see the example of the flow in the pipes and how it's behave different. And we need to use the CFD to understand what's happening on these multi-phase flow. The another one is the CFD application, the combustion. This is also one of the uh, open research area. Combustion is the highly intricate process that involve over 100 spices and reaction rates. Therefore, it's a complex phenomenon, and it's depend to the we can say the material or the fuel for the combustion, if we call it. We have the gas combustion, gasoline engine, gas burner, spare combustion, jet engine, diesel engine, combustion of the solids, coal, wood, and polymers. And also, at the current time, one of the complex problem the scientists dealing with it also, and it's important for the industry and the sustainable energy and climate change also, it's the hydrogen. For the hydrogen, indeed, there is not known equation or solution that how the combustion is happening. From the experiment, it's very difficult and it's hazard area to have the experiment with the hydrogen, especially with the big engine or with big combustion. Therefore, the CFD is the one of the main solution which is working to simulate the hydrogen flame and combustion. And there are many different studies. And without the high performance computing, it's not possible to run the simulation of the hydrogen. And also to have an example of the application of the deep learning. Also recently, there are some studying they are using deep learning capability to study the combustion of the hydrogen. For example, using the convolutional neural network, making experiment of the combustion with a small flame and taking time series of the picture, and then using the capability of the CNN to see how during the time the flame of the hydrogen is changing and what's happening in this area. Uh, Therefore, this example of the CFD of the combustion, it's also showing the importance of these application. As we said in the previous slide, the CFD basically has a fundamental concept of the Navier-Stokes equation. Navier-Stokes equation is for Newtonian fluid and incompressible flow. Indeed, these equations are second order nonlinear partial differential equation PD and quite formidable, especially for turbulent flow. For the laminar, here you can see in the center of this slide the presentation of two different regimes, the laminar flow and turbulent flow. As you can see, for the laminar flow, the flow it has a streamline very uniform, and we can follow the flow, and solving the laminar flow it's much easy and possible. But when we look on the turbulent flow, which is the second picture, you see they have a nonlinear and a random motion, and it's very difficult to solve this data, and it depends also to how much of the uh, turbulence intensity of the turbulent flow, which is measured by Reynolds number. When we have a higher Reynolds number, that means the turbulence intensity higher and the complexities get higher. Dealing with the turbulence flow, it's too difficult. And you can see the presentation of the Navier-Stokes equation also in this slide. To solve this equation, to understand the solution of the problem, the equation have four unknown, pressure and velocity in three components. They should be combined with the incompressible continuity relation to form four equations in these four unknown to be able to solve. And this is one of the closure problem that we have in the turbulent flow. The Navier-Stokes equation have only a limited number of the known analytical solution. That means mostly we solve this equation computationally or numerically. It is possible not to achieve approximate but realistic CFD result for a wide variety of the complex 2 and 3-dimensional viscous flow. About the numerical method and scheme used on the CFD, the finite difference one is for the simple geometry. We have the finite volume, which is used in the complex geometry, and most of the software using the finite volume. We have the finite element. Finite element, one of the stock approach, how it's mathematically it's complex and is started for the solid object. In the lecture that we will talking with the solid object, we will talk in detail about the finite element and what its advantage and disadvantage. There is a spectral element, a spectral method, boundary element, and a reduced method, and all of them used on the CFD to solve the problem domain in this area. About the numerical method, as we said, we have the finite difference method. It is simple, straightforward to apply, usually for regular grid. Finite volume used for irregular mesh grid, and final element method is structured and unstructured grid. Most difficult and sophisticated computation, as we said. Finite element method solve any problem with differential equation. It is complex method. Here you can see the difference between the structured and unstructured domain that we need to create a grid for them. Because of this complexity, so the computation will be higher, and you can see in the unstructured example, the meshes has a different size, so we don't have a regular grid to solve the problem. Then this complexity, as much as we have, it's make the computation higher and more costly when we are using the high performance computing. Here, the first part of this lecture is finished, and there is a video. I suggest you to watch it to see the application of the CFD for the aircraft, and it's studying the aerodynamic performance of these industry. In the second part, we will continue this lecture and we will talk about some other concept and application of the computational fluid dynamic. So I'm leaving this part here, and I will continue this lecture in the second part. Thank you.